Okay, so this is a quick video about dipoles. So a dipole just means you have two charges, opposite sign. They're separated by some distance. I'm calling the distance 2d here because we're going to do a bunch of math with it, and often the math will depend on half the distance, and I don't feel like writing a bunch of 1/2. So anyway, these are the dipoles. They're separated by some distance d. We've already looked at the fields of dipoles. They look something like this. This video is not so much about looking at what the fields look like. This is going to be a pretty mathy video, and it's just designed to kind of show us how to calculate things about dipoles. Okay, and so one other thing is that dipoles have what's called a dipole moment. And this is a vector. You can see that I have that little arrow there, and it points from the negative charge to the positive charge, and it's defined as the charge and the distance between them. So I've got a plus charge here, a minus charge here, but they're both q, right? And my distance in this case is 2d. So you're going to see this popping up a lot. It's kind of a shorthand way to save yourself from writing some steps, but it's also physically an interesting quantity too. The reason why it points the way it does is because when you're outside the dipole, that's the direction of the electric field. Another thing that's interesting about it is, let's say that you have a dipole that is, let's say, randomly oriented. If you place it inside of an electric field, the dipole will rotate so that it orients with the electric field. So that's another interesting property of dipole moments. Another thing is, let's say you have a neutral atom. You know, you've got a nucleus and you've got electrons flying around the nucleus. This has no dipole moment, but if you put it inside of an electric field, the atom will polarize, and you'll end up with perhaps the minus charges a little farther to the right than they were originally. Okay, and so now what you've done is you have polarized this atom, and there's actually even there's a polarized, this is outside the scope of this video, but whatever, there's a little thing called alpha, which is the polarizability. It varies from atom to atom, and it's a good way to talk about different kinds of atoms. Different atoms will have different dipole moments when you put them in electric fields based on the way the protons and electrons interact with each other. Most of what we're interested in this video, though, is not the internal stuff that goes on inside the dipole, it's the external stuff that goes on outside the dipole. So let's see what that looks like. What we're going to do is we are going to look at how to calculate the electric potential first in 1D, a distance x from the axis. Okay, so we know the potential for a point charge. So we have 2 point charges here, and if we want to find the total potential, we just add them up. The potential from the plus charge plus the potential from the minus charge. And so I've labeled the distances. The plus charge is a distance r plus, the minus charge is a distance r minus, and we can write those distances pretty easily. And this is, believe it or not, the electric potential of a dipole along the axis. Okay, so if I look at cases for x very large compared to d, so we're saying pretty far away from the dipole, which actually makes sense because atoms are very small after all, then the electric potential looks something like this. So it looks like the potential of a point particle, except instead of going like 1 over r, it goes like 1 over r squared, which kind of makes sense because there's some potential cancellation. This guy is negative, this guy is positive. The positive guy's a little bit closer, and so they don't cancel completely, but the field, the electric potential, is a little bit weaker than it would be otherwise. Okay, so that's the potential. If you wanted to calculate the electric field from the potential, well, that is the derivative. Potential is defined as the integral of electric field, and so the electric field is the derivative, and if you take a derivative on that, you get this as the electric field. Notice I keep using this p guy because I've got a dipole, and so typically these things are expressed in terms of the dipole moment. That's the electric field. It points to the right, as we would expect. That's what that x hat piece means. And so this works great. You might say, well, fine, what do you do with this? Okay, well, here's what you do with it. If you're curious to know, if you put a positive charge there, some point particle that has a mass m and charge q, we know that there will be forces on it. And we might say, okay, how does this thing move as a result of those forces? Okay. In fact, what if we said, how fast is this thing moving after a very long time? Okay. One way to solve that problem is to find the force, by QE, and then set that equal to mass times acceleration, which is the second derivative of position, and you've got this. This is a differential equation, which you are more than welcome to solve. Have fun with it. I have no interest in doing that, and so we are going to use potential to do it instead. That's actually why people prefer to work with potentials. This is really hairy to solve this differential equation. It's much, much easier to solve this problem instead using potentials. So what we're going to do, potential is potential energy per unit charge. So if we can use conservation of energy to solve this same problem, that's what we're going to do. And so we can set that up. We can say the final speed minus the initial speed, or the kinetic energy, that's equal to the change in potential energy. Potential energy is QV, right? QV at infinity is 0. Whenever you're infinitely far away from charges, the potential is 0, just like the electric field is 0 too, right? The nice thing here is that this equation doesn't have any derivatives in it, so we don't have to do a differential equation, and there's no vectors. So in 1D, that's not so important, but in 2 dimensions, it becomes very important that it's not a vector. It's much easier to work with, okay? And so I can just write this down, a half mv final squared equals, and then I just copy this thing. Right, I just copy this thing, and I'm done. And then you do a little bit of algebra. You plug in whatever m, q, and x you have, and you can very easily find the speed very, very far away. Okay, so much for that. That's 1D. So now let's move to 2D. Okay, this is 2 dimensions, and this is right above the midpoint. Right above the midpoint, some distance y. Okay, so let's actually do the same procedure we did last time. It's a little trickier this time because we've got triangles instead of straight lines, but it's still the same idea. V of r is v plus v minus. If I plug in for the r's, I've got d for each side, y for the top. So if I plug them in, it looks something like this, and the potential is 0. Okay, so it's 0. In fact, it would be 0 anywhere along a line between the two, and we know that from looking at pictures of equipotentials for dipoles. There's an equipotential that runs right along the center. There's a funny thing about this, though. If we decide to calculate the electric field up there the same way we did last time, well, we're taking derivatives, and the derivative of 0 is 0. So that's not good. Something has gone terribly wrong here. We know that there's an electric field there because the plus charge makes that, the minus charge makes an electric field that looks like that, and their sum looks like this. There's definitely a non-zero electric field here. So we've done something horribly wrong. Those of you who are math savvy might recognize that we have plugged in a particular value, x equals 0, in order to get this. And we took a derivative once we had already plugged in. This is the equivalent of like when they say, what's f prime of 3? If you take f of 3 and then differentiate it, you're going to get 0, of course. What you need to do is take f prime of x and evaluate at 3. Okay, so that's the trouble we're running into. We are trying to differentiate a constant. What we need instead is some formula that tells us the potential for any x. So let's do that. It's going to be a little uglier, right? But this is for some random x and some random y. We can set up the same potential we did before. We can set up all the same things we did before. Only now, instead of a d squared, we have x minus d. So x is the distance measured from the midpoint. So this is d. And so, for example, this is x minus d. So the terms look a little bit different now. They certainly don't cancel anymore because their denominators are different, okay? So if we want to find the electric field now we can use our trick. And if we take those derivatives, we end up with something that looks like this, which admittedly is not pretty. It's not pretty, but it's pretty straightforward to calculate. And if I want to find those fields I was talking about before, well, I can say for x equals 0, that's right along the midpoint, that's here. I can plug in x equals 0, and I end up with this. It's that field that I was looking for before. As another good test, let's find it along the axis and see if we get the same value we did last time. So if I plug in y equals 0, well, then I get something that looks like this, which doesn't look very much like what we had before, but we can make some simplifications. Okay, and if we make some simplifications, then we end up with, for x much, much larger than d, we end up with the exact same formula that we ended up with before. So I admit that this is quite messy, but it gives us the result that that we found earlier, and this formula is generally applicable. Now the question is, okay, well, fine, what do you do with all this? Okay, same thing you did before. Put a particle there. That particle is going to feel a force. If you want to talk about the motion of the particle, you can use F equals ma, which I don't recommend because then you solve differential equations, and in fact you've got two differential equations to solve here because this thing is being pushed in 2 dimensions, right? Or we say, well, let's first make a simplification. We'll say, all right, this potential for x and y big looks something like this, okay? And so we'll do the same thing we did before. If we want to know how fast this thing is moving when it's far away, delta ke plus delta pe equals 0. Same formula I wrote on that first slide where it was nice and easy. The formula just looks a little bit different now, that's all. But that's the beauty of potential. This is a much more complicated problem. And my formula just gets shifted just a little bit. If you go back and you compare that with the first slide we looked at, it's pretty much the same thing. Same amount of difficulty anyway. Whereas if you go back and you look at the electric field that we would have had to work with, mamma mia, I definitely do not want to do anything with that. Okay, so that's a rough idea. So what do you do with a potential from a dipole? You use it to find the speed of a thing when it's far away. All right, hopefully this was more helpful than confusing.